All right, good afternoon, everyone. I am Jiang at Recourse, and I'm the chair of the final session. So we have session 5. Welcome to session 5, Algorithm, Fairness, and Resources. And thank you for staying with us, for the final session of the day. I know it's been full day and very stimulating discussions, and I really appreciate your energy and engagement. So we have 4 presentation in this session, and each presentation, like others, will be 20 minutes, 12 minutes, and followed by 3 minutes of discussion and questions. So I'll give a 2-minute reminder before each end of each talk. So let's get started. Please join me in welcoming our first speaker, Kuan-Chieh. Kuan-Chieh. So he's going to present FairWAG, Fairness Aware Weighted Aggregation for Graphic Learning in a federated setting.
Yes. So hello everyone, I'm excited to present our work here. So this is a joint work with Yuntian, Yuze Jiang, and my advisor, Srinivasan Parthasarathy from the Ohio State University. So let me start by introduce the background of this work from the perspective of equity in AI system. So AI systems are increasingly making decisions that affect people's life and social economy outcomes. For example, we are seeing AI used in finance, housing, healthcare, so on and so forth. However, the risks are high because biased AI system can deny the opportunity to underrepresented groups and even amplify the existing inequality in our society. So in this work, we propose FairWAG, which is a fairness-aware weighted aggregation framework designed specifically for federated graph learning. It's tackled structural bias in graph data and the critical challenge of heterogeneous demographic across clients in the federated learning setting. What makes FairWAG practical is that it provides a scalable solution for demographic fairness across decentralized data. Think about hospitals that cannot share patients' data, or government agency with privacy constraints. This organization needs to collaborate on AI systems while maintaining the fairness. Yeah. So now let me briefly explain how standard federated learning works, so you can understand what our proposed FairWAG building on. In the standard federated learning, the process is very straightforward. First, each client trains a model locally on their own data. Second, these clients send their model updates to the central server, sorry. And then third, the server aggregates these updates in the basic setup. This is done through simple averaging. And fourth, the server sends these updates, the updated global model back to the client. And we call this process one aggregation round, and the process repeats. Now, here is where FairWAG comes in. When the server aggregates the model updates, if the aggregation methods don't account for the heterogeneity across clients, and weights them appropriately, then the bias gets incorporated into the global model. So with the context, let me walk you through how FairWAG works. As you can see from the figure, this figure illustrates how FairWAG process in our in one aggregation round. Consider a federated learning framework with n clients. Each client maintains its own data locally, and we can see heterogeneity across these clients' data. In the aggregation rounds, the client train locally on their own data and then sends the updated model parameter to the server for aggregation. Up to this point, FairWAG follows the same process of standard federated learning. Where we make differ is at the server-side aggregation step. This is where we intervene to ensure fairness. So FairWAG leverage a small proxy validation dataset at the server side, which maintains a relatively balanced demographic distribution. And then by using these proxy datasets, FairWAG adopts a dual level weighted aggregation. So we have client level weighting and neuron level weighting. Since bias shows at multiple scales, FairWAG reweights the model updates from coarse to fine. The idea is that we want to upweight the client with which maintains less biased data and positively contributes to fairness in the global model. At the same time, we want to downweight the learned model parameters at each client that are sensitive to the sensitive attributes. So now let's first look at the client level weighting. At this level, we addressed data heterogeneity by adjusting how much each client contributes to the global model based on their data distribution, data structural bias and contribution to fairness. So we're focusing on two components. One is the group balance score, which quantifies structural bias in the graph data at each client. This helps us understand how balanced or how skewed each client's data is. The other one is the client contribution, which we measure by using Shapley value. Shapley value is a concept from collaborative game theory that attributes the marginal contribution when multiple parties work together. So in our context, it helps us determine how much better or worse the global model would perform without a specific client. And this tells us how much each client should contribute during aggregation. Now let's look at the neuron level weighting. At this level, we adjust individual neuron parameters based on two types of importance. One is the utility importance, which measures how much each neuron responds to class relevant features. So in other words, neurons with high utility importance are more activated during the prediction task. The other one is fairness importance, which quantifies each neuron's sensitivity to sensitive attribute. If a neuron behaves differently for different groups, it means that neuron could contribute to bias in model, and we want to reduce this kind of correlation. So we upweight the neurons that have high utility importance and downweight neurons that are sensitive to sensitive attributes. And lastly, we update the global model. We first trace the difference between each client's current local model and the previous server model as a pseudo gradient. And then the server perform weighted aggregation using the pseudo gradients scaled by both client level weights and the neural level weights we got previously. So in this work, we test FairWAG in two different experimental setups. First, we have controlled heterogeneity experiments using the POC-N and POC-Z datasets. The task here is to predict whether a user is working in a field. The sensitive attribute we consider is either gender or the region that the user belongs to. In this setup, we vary the number of clients, testing with 2, 4, and 8 clients with different level of demographic skew. As you can see in the table, we control the demographic heterogeneity using parameter alpha. When alpha is 0.1, we will have a extreme skew, like client 1 has 90% of one gender. When alpha comes to 100, the distribution is much more balanced across clients. In our second experimental setup, use the ACS income datasets. This is a dataset curated US census data from all 50 states plus Puerto Rico. And this gives us a realistic federated learning scenario where each state has its own natural demographic distribution. The prediction task is to determine whether an individual annual income exceeds $50,000. In the experiment, we consider two sensitive attributes, either sex or race, and we convert the ACS income dataset from tabular data to graph data by linking individual with high feature similarity. To evaluate the performance, we assess both utility and fairness. For utility performance, we simply measure accuracy, higher the better. And for fairness, we use two standard metrics. One is the statistical parity difference. The other one is equal opportunity difference. For both fairness metrics, lower value means more fair, ideally close to 0. So our goal is to maximize the accuracy while minimize both fairness metrics. This is the performance fairness trade-off we're trying to optimize in this work. So we include comprehensive experimental results in this paper. Here we only present the result from ACS income datasets, which represent the real-world feature learning scenario. So look at the curve over training rounds. We can see FairWAG in pink maintains competitive accuracy while significantly reduce both fairness metrics. So the result shows the robustness of FairWAG to different fairness consideration in real-world setting. Now, let me quickly summarize the conclusion of this work. First, we validate FairWAG on US Census dataset and social network datasets. The results suggest that it's highly applicable to government and NGO contexts where data heterogeneity is the norm. Second, FairWAG uses interpretable fairness metrics that can inform policy audits and compliance framework for AI fairness. And finally, the experimental result shows that removing sensitive attribute or client level debalancing alone is insufficient, highlighting the needs of systemic model level fairness intervention is necessary. Yeah. So before ending, I would like to acknowledge the support from the NSF grant that enabled this research, and thank you.
A great presentation. I think we have time for 2, 3 questions from the audience. Can I ask one question while we are waiting? Yes.
Yes. Thanks for your presentation. I mean, in the slide 10 that you showed, there are a couple of notes about the sensitive attributes. So I guess you just only considered binary sensitive attribute here. Yeah. So I mean, is this framework currently can be adapted to multi-sensitive attribute groups, or I mean?
Yeah, this is a very good question. So currently in this work, we only consider binary groups in our sensitive attribute, but it's very easy to extend to multiple sensitive attribute groups just by like modifying the matrix, the fairness matrix definition, then it could be extended easily. Yeah, and it's a good direction for like extending this work. Thanks.
Any other questions?
Good talk again. I just had a question about the fairness metrics you used. You mentioned that you used the two and you mentioned interpretable fairness metrics. I was
Yes.
wondering, how are other fairness metrics not interpretable? Like, why were these two just chosen for the task?
Okay. So the statistical parity difference, which we assess the disparity in positive prediction rates between different groups. So these metrics can help us like ensure different groups are treated similarly. And the other one is equal opportunity difference, which is measuring the difference in true positive rates between groups. So this ensures that the individual from different groups receive equal benefits when they are deserving a positive outcomes. Yeah.
Right, I think we're about. Any more questions? All right, thank you so much.
Thank you.
for the presentation.